Good morning, class. I'm going to try and do a live stream and see how well that works. Wasn't working very well when I was in Edmonton. I'm going directly from the data on my phone. We'll see how much data that cost me. The homework we had last night was 18, 13, and 15, but then I realized after I looked at it that I had already done 18, 13 with you. So I'm going to do 18, 14, and 15 with you. And it'll give you the practice you need to understand how to calculate the partial pressure of gases, which you should already know because we already covered it in the last chapter. We did it in chapter 20. Anyway, from the data in table 18.1, what is the concentration of neon in the atmosphere in parts per million? B, what is the concentration of neon in the atmosphere in molecules per liter, assuming an atmospheric pressure of 743 torr and a temperature of 300 Kelvin? Today is day 29 of Coronachem. And this is period 1, which is for grade 11, U and AP, and also for college, grade 12. Today, the date is May 14th of 2020, and it is a Thursday? Today is Thursday. So neon is 18.18 parts per million, according to the table. Which I looked up. So that works out to 0.4 zeros, 1, 2, 3, 4, 18, 1/8 of a mole per 1 mole of air. If you multiply that by Avogadro's number, it gives you, this is 6.02 times 10 to the 23, in case you don't know. This is 1.0948 times 10 to the 19 atoms per 6.02 times 10 to the 23 atoms. And we're going to set that out to x over 10 to the 6, which is a million. Or so we can simplify that to 6.02 times 10 to the 23x equals 1.09, etc., times 10 to the 19 multiplied by 10 to the 6, or 18.2 parts per million. Oh, I think they were giving you the mole fraction. That's what it was. Table 18.1. Let me just clarify that because table 18.1. That's 18.2. Table 18.1. It says neon. Neon has, there's 4 zeros, 1818. So we've converted it into a parts per million. It's 18.2. Still no viewers. I guess you guys, I haven't kept my hours, so you don't know I'm broadcasting. I hope I can upload after this. It should upload. Part B. That was part A. Part B, it asks, what is the concentration of neon in the atmosphere in molecules per liter, assuming an atmospheric pressure of 743 torr and a temperature of 300 Kelvin. So we're going to use PV equals nRT. We'll rearrange for the number of moles, so N is equal to PV over RT. And we have 743 760ths of an atmosphere and 1 liter of air. The gas constant for this is 0.082057 liter atmospheres per Kelvin mole. And the temperature is 300 Kelvin. So that gives you 3.97, 135, 1536 times 10 to the minus 2 moles. If we multiply by it's moles of gas. And if you take that number and multiply it by the proportion that it represents of that gas, which is 18.2 parts per million, what you get is times 0.40 is 1, 2, 3, 4, 1818, turns it into 7.2199 1709 2 times 10 to the negative 7 moles per liter. So that equals 7.22 times 10 to the negative 7 mole per liter. And another way of saying it is if you multiply by 10 to the 9 nanomoles per 1 mole, it comes out to 722 nanomoles, or billionths of a mole, 722 billionths of a mole. Let's try 1815. The dissociation energy of a carbene-bromine atom is typically about 210 kilojoules per mole. What is the maximum wavelength of photons that can cause the carbon-bromine bond dissociation? This is a matter of practical importance because in the old days they used to use chemicals that had bromine and fluorine and chlorine in them, which were thought to be inert, which is why they were used. But as it turns out, if you expose them to ultraviolet radiation of a sufficiently short wavelength, it actually can dissociate the bonds, and then you get you get a catalytic destruction of the ozone layer, and it proceeds by a free radical mechanism because the bond breaks in a peculiar way. It's not like both electrons go with one or the other atom. What happens is the two electrons split, and you get an unpaired electron on each species, and both of those are highly reactive. And they're going to look for a partner as quickly as they can. And if it happens to be ozone, then ozone is what they're going to pair up with and destroy. So the bond energy is 210 kilojoules per mole. Now, if we multiply that by 1,000 joules per kilojoule, it converts the quantity to joules per mole, 210,000 joules per 1 mole of substance, times 1 mole per an Avogadro's number of bonds, 6.02 times 10 to the 23rd. So what you get is 3.487 13198 times 10 to the negative 19 joules for 1 bond to break. Now, I showed you on the first class that the energy of a single photon of light, this is the content of chapter 6, so I don't expect you to know that. You're just going to have to accept my formula for this, and they give you a formula that works. The energy contained by a single photon of light can be discovered by using this equation. Energy is equal to a constant called Planck's constant times the frequency of the light. Every different color of light has a different frequency. Just like you can tune to different radio stations, you're actually tuning into a certain wavelength. And then when you get your radio to tune into the exact wavelength that resonates at the right frequency, then it can transduce that electromagnetic radiation into sound. That's what the purpose of radio is. It captures the electromagnetic waves that are being broadcast from distant radio towers and turns them into something that we can hear. We're constantly bombarded by electromagnetic radiation. We're only able to perceive the visible part of the spectrum, which is wavelengths between 400 and 750 nanometers. But there's plenty of other wavelengths in every direction to either extreme of the visible spectrum. So beyond 750 nanometers, you have microwaves and radar and radio waves, and below 400 nanometers, you have ultraviolet light, you have X-rays, you have gamma rays. They're all forms of light, but we can't see it. They exist, but we can't see it. So we're solving for the frequency of a light, of a photon of light that has that much energy. So we're going to rearrange the equation to solve for the frequency. So the energy we know, we just calculated it. Planck's constant is a known number, and the frequency is going to be represented by the letter V, which we call nu. The letter nu, the Greek letter. So 3.487 13198 times 10 to the negative 19 joules divided by 6.62607,004 times 10 to the negative 34 joule per second is Planck's constant, and the frequency of this photon is going to be 5.262,745,43 times 10 to the 4 seconds to the minus 1. So if now we use the wavelength, which is represented by this symbol, which is called lambda, times the frequency equals the speed of light. We know the speed of light, and we just figured out the frequency, so we can find out the wavelength by doing this. So therefore, the wavelength lambda is equal to the speed of light divided by the frequency of the radiation. And we'll plug in the numbers again. 2.9979 2458 times 10 to the 8 meters per second divided by 5.262,745,43 times 10 to the 14 seconds to the minus 1. So lambda equals 5.696 50313 times 10 to the negative 7 meters, or if you like, multiply by 10 to the 9 nanometers per 1 meter, and you get 570 nanometers after accounting for the sig-figs. So 570 nanometers, that would be a visible photon. You'd be able to see that light. Okay. All right, enough of those mathematical treatments. Let's go over some of the other ideas I want to share with you. It's the composition of the troposphere. That is the lowest layer of the atmosphere. Lowest layer of the atmosphere extends from 0 to 10 kilometers altitude. It is where most of the air is located. 75% of our atmosphere is located in that part of the atmosphere. The atmosphere thins progressively as you gain altitude, and when you get to extreme altitudes, in fact, they put satellites very often at a height of 100 miles, which is 160 kilometers, because there's very, very little air molecules by that altitude. So the fewer air molecules that are present, the less drag the satellite that's orbiting the Earth experiences. Now, the satellite has to orbit the Earth once every 88 minutes or so, and which means it's going very fast. So any molecules that are up there are going to slow down, because once the satellite passes through through the space where the air molecule is occupying, it's going to transfer its momentum to the air molecule. Now, molecules are very small, so very little momentum is transferred, but if it happens for long enough, it causes decay on the satellite's orbit. And eventually all satellites do decay in their orbits and they come crashing down again, although it can take decades for that to happen. Okay, going to the composition of the troposphere. The troposphere, which is extending from 0 to 10 kilometers altitude, is 99% nitrogen and oxygen, but also contains CO2, carbon monoxide, methane, nitrogen monoxide, ozone, and sulfur dioxide. Now let's look at some of these other substances, some of which can be referred to as pollutants. Carbon dioxide, definitely not. Although it's sometimes demonized, carbon dioxide is actually necessary for plants to live. CO2 is plant food, so it's not a pollutant. These other ones, if they're at lower altitudes, could constitute pollutants. For example, ozone is not good at sea level. It's toxic. It's best it stays at higher altitudes, but it can be produced by industrial pollutants. Let's look at sulfur dioxide first of all. Sulfur dioxide and also oxides of nitrogen contribute to the formation of acid rain, because what happens, for example, with sulfur dioxide is that it combines with, well, first of all, it can combine with water, in the atmosphere, and you produce sulfuric acid. There's probably an intervening step there where it combines with oxygen as well, so you get sulfur trioxide. The process is not clear to me. I don't know the exact mechanism, but you get sulfuric acid. I don't know what the stoichiometry of the reaction is and whether there are intervening steps. SO3, for example, in the book, it says this. Now, sulfur dioxide is probably an intervening step where some oxygen is added first, and then you get SO3, and then from SO3 you get sulfuric acid. But suffice it to say, it produces acid rain. With oxides of nitrogen, you get a similar reaction where you get, instead of sulfuric acid, you get nitric acid. They have scrubbers installed in smokestacks. Now, smokestacks are going out of style because they're known to create pollution, but they used to install scrubbers, which were chemical reactions that would pull the sulfur that was released from burning coal so that it wouldn't go into the atmosphere and cause pollution. Another atmospheric pollutant is carbon monoxide. It is relatively non-toxic to plants, but it binds very avidly to hemoglobin. Even very low concentrations of carbon monoxide can be deadly, as I mentioned, I think, in the last lecture. Nitrogen oxides, or nitric oxide, forms when air is heated to high temperatures. So when your car is driving, the air is being sucked into the engine so that you have oxygen so the fuel can burn, but also the nitrogen gets sucked in because the atmosphere is 78% nitrogen after all. So when you expose nitrogen to high temperatures and the presence of oxygen, some of the molecules can combine into nitric oxide, which is NO. And nitric oxide and also nitrogen dioxide are both toxic chemicals. So over the years, scientists understood this, and it was slowly mandated that vehicles have to have a catalytic converter. It's a bulge in your muffler near the front of the car. So let's call the muffler that big long tube that extends from the engine all the way to the back of the car. Really, the muffler is the big fat part at the end towards the back of the car. But coming out of the exhaust manifold, which is the hottest part of your exhaust system, they usually have another bulge, which is smaller than the bulge of the muffler, which contains platinum catalyst to help break down the nitrogen oxides back to nitrogen and oxygen. In fact, those catalytic converters, as they're called, have been the object of theft because of their platinum content. They're relatively valuable, so sometimes people will cut them off the cars that are parked in large lots, and they end up stealing and obviously destroying the value of the cars, because then you have to make them road legal and road worthy again. You'd have to reinstall a proper muffler, and you can imagine it's not very cheap. So what else? Probably the most important substance in the atmosphere is water. Water helps to trap heat near the Earth's surface. It is the most important greenhouse gas. So does CO2, but there's much more water than there is CO2. The apparent temperature of the Earth from space is only 254 Kelvin. It's about minus 20. So why is that? It's because the water vapor traps most of the heat near the surface, and thank goodness for that. Otherwise, it wouldn't be very pleasant to live on the Earth. Methane is also increasing its effects as a greenhouse gas. It's actually more powerful than carbon dioxide. And the greenhouse effect may save humanity eventually. There's a twist on the usual panic that you hear from climate change, because we are about to enter an ice age. We're due for an ice age. We haven't had an ice age for the 12,000 years, and the pattern has been 40,000 years of ice age and about 10 to 12,000 years of warm period. So we've had 10 or 12,000 years of warm period. So if the pattern holds, we should be entering another ice age soon. And this is no small matter, because in the last ice age, the ice sheet was over a mile thick on Canada. The city of Toronto would have been under a glacier. And they alter the landscape dramatically. They crush everything under them. They drag boulders miles away from where they were, and they crush up the landscape, and they tend to strip the soil, and then it takes thousands of years for it to recover. It's not something you're going to see in your lifetime. If you were to enter an ice age, it's not like you'd say, "Oh, here comes the ice age." It would take several lifetimes for it to happen, but there would be a gradual cooling trend, and perhaps there'd be fluctuations where it would get hot for a while and it would get cold for a while. So there would be a countervalence of forces until one of them won out, and then you entered the ice age in earnest. That seems to be happening. People are talking about climate change. This climate change is going to, when has there not been climate change, basically, that's what I'm saying. Greenhouse effect may save humanity from entering the next ice age. Maybe it's a good thing. If you don't want to enter an ice age, maybe we should increase the carbon dioxide. Who knows? Maybe humanity will come around. Once we have snow in the summer, we might change our mind about greenhouse gases. We might say, "Hey, wait a minute, snow in July is not such a good idea," and maybe we'll be more open to the idea of fighting the next ice age. I don't know how prudent that is. Well, that's time will tell, but we'll all be long dead, so don't worry about it. About water, the Earth's surface is 72% water, and that's a lot. It's a lot of space. Hydrogen bonding causes water's high melting and boiling point. One of the most amazing things about water, it is really an amazing compound. If you take a look at it, if you analyze it, it's made of hydrogen and oxygen. Hydrogen boils at something like minus 265, 270, and and oxygen boils at minus 186. So how is it that water boils at plus 100? Why is like a 250 degree or more temperature change difference between the boiling points of the constituents of water and water itself? And that's because water has the peculiar property of hydrogen bonding. So if you look at water, because the hydrogen and the oxygen have different electronegativity values, the electrons spend more time closer to the oxygen. So the oxygen has a slight negative charge and the hydrogen has a slight positive charge. Actually, you could say two negatives because it's contending with two hydrogens. So because of that dipole, that's what it's called, you get a charge, unevenness of charge, water molecules like to stick to each other. They have an attraction. The oxygen atom of one water molecule will be attracted to the hydrogen atom of a water molecule close to it, and likewise the hydrogen atom of the same water molecule will be attracted to the oxygen atom. So they create a slight bond which increases the melting and the boiling point of water to a higher point than you would think it should have based on the substances that it's made of. And hydrogen bonding has many effects that we probably take for granted. For instance, it increases the volume of ice. So that what happens is the density of ice is lower than the density of liquid water. So ice floats. Could you imagine if ice didn't float? Every winter, all the fish would die because they would get crushed by the ice forming on the surface of a pond. The second interesting thing about water is it creates surface tension. If you're a small insect, the surface of water is almost like a sheet of plastic to you. It's hard to actually break through the surface because the water molecules stick together strong enough that you can actually walk on the water surface if you're light enough. You've seen water striders, they can actually walk on the surface of the water and you see the water bending around their leg, but not wetting the leg. And that's a clear demonstration of the surface tension that results because of hydrogen bonding. The other thing that's really cool about water is it can interact with the system of irrigation that trees have. Trees, ever wonder how trees can pull up water all the way to the top of the tree? If it was by a vacuum action, you would not be able to get a tree growing higher than 32 feet because atmospheric pressure would put a limit on how high the water would push up into the tree. But there's other forces at work, and one of them is capillary action. So the water actually hydrogen bonds to the inside of membranes that pull the water up into the tree, and so the tree can be of any height you would like because that capillary action helps the water to adhere all the way up to the top of the tree. And then, of course, because water has a high specific heat capacity, it actually has the highest specific heat capacity of any substance known. Because it has that high specific heat capacity, meaning it takes a lot of energy to make water change temperature, water acts as a great temperature buffer. So if you live close to a large body of water, it modifies the winter's lows and it modifies the summer's highs. So it keeps the weather from getting too hot during the summer, and it prevents it from getting too cold in the winter, because during the winter time the water is emitting heat energy that it gathered over the course of the summer. So a large body of water has a lot of heat energy stored in it, and as it cools down during the course of the winter, it actually releases heat energy. And in the summertime, it's absorbing heat from the sun, and it helps to also moderate temperatures. So if you live near a body of water, temperatures tend to be more mild, more temperate. All right, that's, I think, enough for today. I'm going to give you just one more practice example to try. I already did 1815 with you. Why don't you try 1816? And I have to show you the question or else you won't be able to do it because you don't have the textbook. So I'll show you 1816. If you can do it, fine. If you can't, don't panic. I will show you the answers tomorrow. So here's 1816. I don't know if you can focus on that. I might not be able to get close enough for the camera to focus it. I'll read it to you. The question is this. In CF3Cl, the CCl bond dissociation energy is 339 kilojoules per mole. In CCl4, the CCl bond dissociation energy is 293 kilojoules per mole. What is the range of wavelengths of photons that can cause CCl bond rupture in one molecule but not in the other. I'll see you tomorrow.